Today we're starting chapter 3, and we're going to be talking about maximum and minimum values and how we find them. They sound obvious, but there's a little bit to it more than just where's the highest and where's the lowest point. So we're going to be using maximums eventually this chapter to figure out what's the least expensive way to pipe oil from an offshore well refinery down to the coast. What's the most effective size for a dose of medication? What's the shape of a can that minimizes manufacturing costs? At what angle should blood vessels branch so as to minimize the energy expended by the heart when pumping blood? And at what speed would you like drive a Durango to obtain the best gas mileage? So some things where we can maximize and minimize topics, very much like what engineers do when they're designing something or manufacturing something at the cheapest cost, that sort of thing. So, an absolute maximum occurs at C if the y value at C is greater than or equal to all other y values in the domain. That makes f of C the maximum value of f on D. So if they're asking where the maximum happens, you can just give the x value, but if they're asking what the maximum value is, you need to give the y. Same works for the minimum. It has to be the point lower than all other y values in our domain. And that would be the minimum value. Where it happens is just the location of the minimum. The y value is the minimum value. So if you see that word value, you know you have to give the y value. So if you notice on a couple of these examples, the absolute maximum is at C, which means the value is f of C, which appears to be about 7. And sometimes you can figure it out. Sometimes you just have to write f of some abstract quantity. Here, our absolute minimum is also at C in that picture. And so the minimum value is C. So, part of my notes got cut off here a little bit, but first thing we're looking for is the minimum value. And if you look at this picture, where is it at its lowest? It's at A, but we want the value, so that's going to be f of A. Where does this graph go its highest? Well, it goes the highest at D, but where does that happen? What is the value? That's f of D. So, if we look at this graph, cosine's the red, and notice we're only going from negative pi over 2 to pi over 2. The maximum of the cosine graph is going to be at 1, or at 0, so it's f of 0, but it is also could be called 1 because we know the maximum y value there. The minimum cosine value happens at plus or minus pi over 2 and is 0 when we're talking from negative pi over 2 to pi over 2. Happens at both of those places. The maximum sine is all the way to the right at pi over 2 where it equals 1. And the minimum, sorry about that, the minimum value of sine is at negative pi over 2, which is negative 1. There are also these things called local maxes and local mins, or sometimes called relative maximums or relative mins. And those happen at C if everything around C has a y value. For instance, a local max happens at C if the y values around C are lower than the y value at C. And local minimum would be if the value at C is lower than the values on either side. It has to be on either side, so it can't be an endpoint as a relative max. So, notice this only has an absolute minimum. That would also be considered a local min. This one has endpoints, so it has an absolute max at this point, absolute min at this point, but no relative mins, because neither of those points is higher or lower than the points on either side, because there is not another side when your graph has endpoints and the graph ends. Here, an open circle and a closed circle. The closed circle is our absolute max, because we could name its y value, we know where it's at. An open circle can't be an absolute min. We know the open circle is at 0, but can you name me the lowest value just to the right of that y value of 0? No. You could always name a number closer to 0, so there is no absolute minimum. And when there's open circles at both ends, like it is on this example, there's no absolute max or absolute min, because you cannot name me the y value that is the highest or lowest. You could always get closer to those y values. Like if this is at 4, 3.9, 3.99, 3.999, we could go on forever. You could never actually name the absolute maximum. X equals y cubed has nothing. Because this is assumed that it goes on forever. At y equals 3x to the 4th minus 16x cubed plus 18x squared, we know it has local mins and local maxes, or here, I'll label them right on the picture. This value right here is going to be a local min. Notice it is lower than the points immediately around it. So this is going to be a local max. This is going to be our absolute max. Could also be considered a local. This point is going to be our absolute max. It cannot be a local because there are not points on either side. And finally, this endpoint is nothing. Can't be a local max because we don't have points on both sides of that point. Extreme value theorem says if f is continuous on closed interval with endpoints at a and b, that's what it means, closed circles at a and b, then f attains an absolute maximum and an absolute minimum value at some numbers c and d in AB. So as long as we have endpoints and it's continuously connected, there will always be a max and a min. There will always be a max and a min. There will always be a max, in this case 2, because they're at the same height, and a min. This function has a minimum value right here, the minimum value, but no maximum value. Notice how that's an open circle? You can't name the largest value, so there is no maximum value. And this last one is a continuous function, but it does not have a maximum or a minimum. This open circle cannot be a minimum. We can't name that value. And this is going on forever next to this asymptote, so we also cannot name the largest value. Take a second, match these 4 pictures at the top with the 4 at the bottom, and pause your video so we can talk about it in a second. All right. You should have A going with the blue box, B with the green box, C with the black box, and D with the red. And there are different things you can use to check there. A, for instance, has no slope at these corners, so we know that the slope does not exist at those points. And we're talking slope here, so slope of 0 at B, this one would work, or this one would work, but we need a slope that does not exist, or no. Slope of 0 at B means that this one would work, or this one would work, but we also need A to not exist. Here A exists, here it does not, so that's how we knew we went with B. So by process of elimination, should have been able to pair all of those up. Now, critical values, keep this in mind, we'll come back to it a lot of a function, is where f prime of c equals 0, so where the derivative equals 0, or where the derivative does not exist. Now, for these next 6 on your notes, I'm going to end the video here. Please spend some time locating local maxes, local mins, absolute maxes, absolute mins, anything you can identify from these graphs, and we will talk about them first thing in class tomorrow.